Okay. Thanks, Eric, for the introduction and invite me to this seminar. So today my topic is about preference robust optimization. So this is a work I've been working for 4 or 5 years along my PhD and postdoc. And this is a joint work with Will Haskell and Jian Wu in Purdue University and Huifu Xu in CUHK. This is today's talk's outline. So I will motivate what is preference robust optimization and what is the problem formulation. And we have developed some algorithms and also some applications for this methodology. So I would like to first motivate this problem by example in literature. It's a Homeland Security budget allocation problem. So now we have 10 US major cities. So they are exposed to possible terrorist attacks. So there's 3 kinds of scenarios. We have reduced loss, standard loss, and increasing loss. And they have followed the same distribution of 1/3. And also, we have 4 attributes which measure the loss of attack. We have 4 attributes: the property loss, fatalities, and air departures, delay, and also the bridge of traffic. So here we denote the random loss in each city for each attribute is Cij. Okay, so this is the problem we are facing. So here is the chart, table 1, which record 10 major US cities and their daily property losses and the fatalities. So they have 3 scenarios, standard, reduced, and increased. And also we record the average daily air departure, delay, and the number of cases of bridge traffics. And by some standard methods in the literature, using the statistic mean value, we can derive a random variable of the air departures and also the daily bridge traffics. So now we have all the attributes as a random outcome. So what is our goal? So our goal here is we have some fixed budget, for example, like $400 million. And we want to invest those money to different cities and for different attributes. And once we do an investment, it will stimulate the economics to compensate the loss. So we define the shortfall, which is a random variable of each attribute as Ciz. So Z is the matrix which we recorded the amount we invested in cities for each attribute. So this will be a shortfall. If our the increasing of the economics value is higher than our loss, it will give us a 0. But if it cannot compensate the loss, it will give a positive loss. So now we have a vector which records for each attribute. Each element is the random shortfall for each attribute. So the question will be how to find the best allocation plan or what is the optimal amount to invest in each city for each attribute. So let's see 2 different allocation plan. So this first allocation plan is want to minimize the expected shortfall. So here is the first table we show, which records the number we try to invest in each city on each attribute. Well, we have another plan is we can equally allocate, we allocate $10 million to each attribute, to each cities. So we compare these 2 allocation plans and what is the random shortfall we gain. So which are recorded in the second table. So the first table is we recorded the result if we using the expected shortfall minimizing objective. And second table, actually this is the third table here, is the result of we do the equal allocation. So we see that for accepted air departures, we find that the expected shortfall minimization will always dominate the equal allocation plan. But for the equal allocation plan, which will do very well to reduce the random loss on the air departures. So the question will be, which one will be better? Which will be one will be good? I think different decision maker will have different preferences over these two plans, right? These two allocation plans. So actually, there's a lot of problems in the literature, which we have multiple attributes, and we need to measure the high dimensional random outcome, like in COVID pension screening, portfolio optimization, and some capital allocation problem. So this is actually from some preference robust optimization literature, which how we motivate the problem. So the first key issue of this decision-making problem is a person or a group of people is account for the decision, and also the performance is measured by is by multiple dimensions or attributes, and also we have a we have a huge number of alternatives to choose. So finally, since we in the last example we cannot tell our preferences over these two outcomes, so the numerical optimization can only can be done when the preferences over uncertainty of decision maker is fully characterized. So when we thinking about the preferences over two prospects, the first model come to our mind is very famous, expected utility, right? So in the expected utility framework, if we have two lotteries or if we have two prospects, so if we say one prospect X1 is preferred by a decision maker than X2, which meaning exists a utility function such that the expected utility of X1 is larger or equal to the expected utility of X2. Well, this model can be used when our decision maker agrees some axioms. So we have 4 axioms here. If he agree these axioms, and we can model his preferences by a utility function. Well, as the theory evolves, as the area develops, so there's some problem when we're using a single fixed decision-making model like expected utility. So the first is we have a game. So I think this is originally from Eric's work. So we have a game. So if a TV show, which we have 4 different options. The first option is we can gain. If we enter the game, we can win $1,000 in with certainty, right? And the D option is we have 5% chance to winning so $10,000, but we will have a 91% chance get nothing. So which one we will choose? So for risk neutral people, for risk averse people, he may choose the option 1. But for those people who is more risk seeking, he may choose D. And also our risk profile will change when the budget on our hand is changing. So if we have more budget on our hand, we will be more risk seeking. If we have little budget, we will be very risk averse. And second, the problem is if we have a group of people making decision, which there must be a consensus using one utility function. And it may be very hard for us to specify one utility function if we have a group of people who have different utility function. And fundamentally, there's some problem when when we apply the utility theory, because people maybe not agree the axioms, even they accept the model. For this game, we call it ally paradox, which was very famous in decision analysis theory. We have 2 experiments, experiment 1 and experiment 2. So we find that if in the experiment 1, people prefer gamble A than gamble B. But if he follows expected utility theory, he must prefer gamble A than gamble B in the second experiment, because in expected utility we assume that the value is linear in the probability, which is a result from the independence axioms. But in reality, people will prefer gamble B than gamble A. So because people have some other phenomenon when they are making decision. So finally is the problem about the probability distribution. So when we use expected utility, we need a value. We need to have a full knowledge of probability distribution. But sometimes when we have a portfolio, we maybe have some historical outcome. So what we can only do is we maybe create some empirical distribution. but maybe very hard for us to get the full knowledge of a probability distribution. Okay, so given all these questions, given the examples and our analyze on the expected utility theory, so we may ask what is the right structure for doing a decision, or what is the right structure for preferences. So this is what we want to answer in this research. So we want to define and formulate new ways of choice and preferences. And in preference or robust optimization, we also want to simplify the assumption on structure of preferences. And also we can review and reduce the uncertainty about the preferences. So finally, we use the preferences learned for decision making. Okay, so we first to model this problem, we maybe go through some tedious mathematics. So here, the only specialty here is we are developing in the space of random variable, which will be a mapping from event space to a vector, right? Like in the homeland security cases. So what we get is a random vector, which the value is on each attribute. So this is a random vector. And also next we define what is a preference order. So if there's a preference order, it satisfies the complete and translative properties, which for complete is we can always compare these two random variables. They are comparable, and translative means if x is preferred than y, y is preferred than z, then x will prefer than z. So based on these two developments, we can define our choice function. So what is choice function? Choice function is simulate how people make decision. So we have some function in our mind which characterize our decision, and we will give a score in our heart, in our mind, when we are exposed, when a random prospects or random variable exposed to us. So if we prefer x than y, meaning the choice function of x is larger or equal to choice function of y. This is quite straightforward. And here we have some global information on the structure of this choice function. So the novelty here is on the quasi-concave. So we assume that the choice function here is quasi-concave functions, which meaning if we compare the compound of two random variables, it's always higher than the minimum of the preference of one random variable, which will be meaning that people will prefer the diversification. And also we have some other information, which meaning the choice function is monotone, semi-continuous, and also lipstick continuity, which will be useful in later in our model development. So this is for all the people. So we assume that all the decision makers agree this structure, agree these axioms. Well, for each individual, our preference is independent, and our preference is different. So how to review individuals' preferences? This is from the local information, and also is from preference elicitation, which with very standard methods in PRO, meaning we have a sequence of pairs of prospects and exposed to the decision maker, and we ask the decision maker which one he prefers. So we use the WK to record the pair the one in a pair he prefers, and the YK is less preferred. And these kind of pairs of prospects can be done, pairwise comparison can be done either in a survey or by historical data. So we use the E here to denote the ECDS pair, which recorded all the data which have been exposed to the decision maker, and he make a choice, make a preferences between the pairs. And also we have some normalization, which we try to fix some value of some fixed prospects. So there are all the information. We are using some data-driven technique to review, to gain some information from individual people. And we have some global information, which is assumptions on our choice function. Okay, so next we introducing the idea called the robust choice function. So since the set of the choice function satisfy both local and global information is an ambiguity set. We know that people follow the local information and the global information, but we don't know what exact the choice function of decision maker is. So here we define the robust choice function. So the idea is standing in robust optimization, we like the worst case paradigm. So here for any random variable x, so the robust choice function is to find the infimum of choice over the ambiguity set of choice function. So also, if we have some benchmark y, we can construct some robust choice functions which measure the distance between some random variable to some target. So yes, we may ask the question why we consider worst case. So if we can do some other mathematical computational processes to gain some counterpart. So the first reason we consider worst case because the quasi-concavity is preserved when we consider the worst case, when we take the infimum. The second is since we are considering group decision making, so taking the worst case, meaning we are choosing some decision or we are choosing some random variable which was favored by all the people, and also it means the least favored people will also accept some decision or accept some results. So that's why we consider the worst case paradigm. Okay, so finally since we are doing a decision making problem, so we complete the formulation of our problem. So first we have some function g. This is some stochastic function, which is a mapping from decision to the outcome. And like if we're in a portfolio optimization, z can be some weight, can be some allocation, and g will be some random outcome of our portfolio decision. And the goal here is we try to maximize the worst case choice function, which will be a maximum mean problem. It's a robust optimization problem. And actually in literature, there's many literature, like if we choose the choice function to be in the class of expect utility or in the class of risk measure, and also we can choose the choice function in the class of some target-based measure, which can represent the prospective theory, which also a quasi-concave measure. So there's some research already have been done. Well, in our problem, we have our own difficulties. So first of all is even there's no ambiguity on the preferences. So this is not a convex optimization problem. So we are dealing with some quasi programming problem. Second is we don't know how our information, our local information and global information can be mathematically explicitly represented in the model. So how can we formalize the model mathematically? So, and finally is we are dealing with a robust optimization problem. So how to come up with some algorithm can solve this maximum problem. So okay, so before we first study before we study the decision making problem, the maximization problem. So now we fix some action z, and we first study the inner minimization problem. So which is how to measure if we give some global and local information, if we have some random variable, how to measure the worst case choice function of this random variable. So this is our first step. So so the idea is called a value problem and interpretation problem. So we first do one process. We use the big zeta to denote all the local information, which W0 is the reference prospects. WK and YK is ECDS pair, which is the random variable exposed to the decision maker. We make them together as a collection, zeta, big zeta. And second thing is now we try to value the robust choice function of a prospects. And we try to think this problem carefully, and we feel that try to determine the robust choice value on the local information on the zeta, and then use the information then to compute the robust choice function of GZ or any other random variable are separate. So we can do it separately, and we can do it independently. So this is the technical two-stage decomposition, which shown by these two figures. The left figure is a value problem. So that each small theta is in this local information. So we have some hammer, and we try to determine the value there. And the second is called an interpretation problem, and we have some approximate function, and then we can see where the GZ, which piece the GZ sits, and the choice function value of that piece will be the robust choice value of GZ. So we do it separately, and then we first we study the value problem. So okay, so before so this is the value problem and the conceptual model of value problem interpretation problem. So for the value problem, our goal here is we only consider the information the prospect has already been exposed to the decision maker, which we are working on the big theta. So we want to find the choice function, which push down the value, robust choice function, which push down the value on the theta as much as possible. And once this is done, and we use the interpretation problem to find what is the exact robust choice function value of any random variable. So this is a two-stage decomposition. And we first solve the value problem and solve the interpretation problem. So the first important theorem is the Theorem 2, which meaning if we do the two-stage decomposition, we use the optimal value solved in value problem, and then use the V star in the interpretation problem. And what we gain, then the robust choice function value solved from the interpretation problem is exactly the original problem. So this is what the Theorem 2 tells us. So we can solve the evaluation problem on any random variable separately. So okay, so let's first dig in the value problem. We go further on the value problem first, and then later on we will study more on the interpretation problem. So before going to the detail, we have some assumptions, which meaning the underlying sample space is finite, and by some existing technique, measuring the robust choice of a random variable is exactly valuing the robust choice of a long vector of realizations. And this is the first main model of value problem. So what's the idea? So the idea is illustrated by the bottom three graph. So okay, yeah, maybe hope you can see carefully. So this is so the blue line here is a quasi-concave function. This is the true preferences of the decision maker. We don't know what it will look like. And then now we can using some I call it a kinkit or like a hockey. When we play hockey, it's a hockey stick type of many hockey stick function, which have two pieces. One piece is which is the slope is positive, is a linear function, and one is a flat function. Okay, we have many these hockey stick type functions which can be measurized. The true quasi-concave function, preference function, we don't know. And the results meaning that if we have local information, we have finite local information theta, and the worst case choice function, and having this local information is always sit in this hockey type shape. So all the worst case function is always lie in this class of hockey stick type. Okay, so the third figure, the most right figure, showing that even our quasi-concave function is not continuous but semi-continuous, we can still using this type of function to approximate it. And here is the main model. So the constraint 1b is showing the quasi-concaveness, okay, on all the theta, and the constraint 1d is the preference elicitation constraints, and the constraints 1e is the normalization constraints. So, and then we are trying to find the function which can push down and as close as to the true quasi-concave function as possible. So this is the main model. So, but this is contrary to, or this is out of our knowledge of convex programming problem, because you see the constraint 1b. So this is a maximize of two things larger or equal to something. So this is not a convex constraint. So then the technique can be used is we can formulate this problem as a binary or integer programming problem. So this is a disjunctive programming. And also, I will not go into detail for the interpretation problem. We can do the same thing. We can formulate it as a disjunctive programming. So here we have a function using a and b to denote where the piece of the random variable x sits. So okay, so for these two problems, both the value problem and interpretation problem, after we explicitly write into mathematical programming model. So the first one has a j square number of binary variables, and the second model have a j number of binary variables. Okay, the j is the number of, is the size of the information, size of the prospects we have exposed to the decision maker. So which meaning the more knowledge we have, the more data-driven knowledge we have, the more computational burden we are facing. And also solving such a big number of MIOP problem cannot ensure the global optimal guarantee. So, okay, so facing this computational problem, we are thinking, is there any way, okay, we can solve this problem more elegantly? So since we are doing the value problem is working on the information big theta. So the goal here is we try to decide the value on the information on the big theta, and all meaning we are trying to do some ordering. We want to know which value function is higher, which value function is lower, and then we can do a preference. We know the preferences of people on this information here has already been seeded. So what if we have some methods which can do the ordering, and each time we want to solve any robust choice function on prospects, we can using the ordering information we already have. So here is the idea. So if we have some order list D, and we have the theta and its optimal robust choice value, and they are ordered. So the DT here means that there's already T value, T prospects has been ordered. And D1 has nothing, and DJ has everything. So our goal here is, if we have some order set, we can progressively enlarging the order set and using the order information to decide the next largest prospects, which has the next largest value. And suppose the DT here is something we have already been ordered, and we want to predict the robust choice value of theta, which theta is not in the order set. This is something we want to order it. And then we can, because we know that the theta will be not favored, will be less favored than the order set, the prospect having already ordered in DT. So we can cut the max in the disjunctive out, and then we can gain something as a linear programming. And then we can using the optimal value of this linear programming problem to construct a predictor of the true robust choice function value of theta. So here is, so if the VT here is in the order set, and this is the lowest robust choice function value in the DT. And the value of a P here is the optimal value of a previous model. And we take the minimum of these two as the predictor of robust choice function of theta. And very interesting, if we force doing this, and we have some algorithms. So at the beginning, we have nothing. We only have the normalization, the zero prospects. And in each iteration, we solve the next largest prospect and put into the order set. Each time we put in one prospect into the order set, and progressively, the size of linear programming will become larger and larger. So the second important theorem, Theorem 3, it tells us that if we're using the decomposition methods, we can find the V star here, which is exactly the original, robust choice function of theta, each theta in the local information, and after solving J square number of linear programs. Well, for MILP, we may require a huge complexity or huge number of linear programs. So it is a very large improvement, and later on we will show by experiment the advantage of this sorting algorithm. Okay, so we're still working on the line of a value problem. So we have a value problem and interpretation problem. So we go in more further on the track of value problem. And second thing is we call it a law invariance. So this is a very common phenomenon for decision making and uncertainty, meaning if two random variables has the same distribution and they have the same preferences. To illustrate the basic idea of law invariance, we have this figure. So we have two pockets. The left pocket have two yellow ball and one red ball, and the right one has two red ball and one yellow ball. So for the left part, if we get a yellow ball, we get $2, red ball for $1, and reversely the result for the second pocket. And for these two pocket, the random variable, if we are blind, we don't know what in a pocket, and we just pick one without replacement. And then the random variable is actually different, but playing the game will be the same. We have the same preferences, interests to play the game both. Okay, then how to model the law invariance. So this is also some standard technique. So the idea is we're using some permutation on event spaces. So since we can assume the probability distribution is uniform, because if we dealing with the finite sample space, consider a uniform probability measure will not have a loss of generality. And then if we consider the normal distribution, and we can play with the 4 permutations on the event spaces. And if we consider law invariance is in fact, meaning if x preferred, then y is equivalent to say the choice function of a permutation of any permutation of x is always larger, equal to the permutation, another permutation on y. So then we can formulate the law invariance version of the value problem and interpretation problem. So yes, so most people, are law invariance. So if we consider law invariance, we actually reduce the conservativeness on the robust model, which will give us some better results. And then the next is we can then reduce this value problem into LP by some technique. So a very interesting thing here is in the constraint 1C. So here n is the number of attributes. So here we are summing from 1 to the n, which together will be a vector. So theta here is the matrix here. So this meaning if the attributes increase, they actually will not affect the computation of this model much. And later on, we will show by experiments seeing that we have a strong scalability on the number of attributes if we consider law invariance of decision maker. And also if we consider law invariance, we can also develop a sorting algorithms we have introduced previously if we have a law invariance, consider law invariance value problem. And then the next question is we may ask is, okay, so why not, because thinking about the law invariance, right? Why not we directly define our choice function, our binary relationship on the distribution on a space of CDF, right? The answer is yes. So we're recently working on this. So why not we directly, define a choice function on a distribution of prospects on actually a random vector. So the difficulty here is we may extend the definition of CDFs to a high dimensional spaces because we're dealing with a multi-attribute problem. So the idea is we try to measure the probability on a lower offense. So x1 and xn is a vector, and we try to measure the distribution on this on the offset of this vector. So other is actually the same as the union attribute cases. So here is if we have some lower ascent order. So if if one one random prospects, one prospect is preferred than another, meaning the CDFs of one prospect is preferred than another, which meaning the choice function defined as CDFs has larger choice function value than the choice function of F2. And then the next question is how to, since we have the definition of CDFs, and how we construct these CDFs. And here is we can define artificially the number of vectors, and we as a breakpoints to compute the CDFs of any random vector. So this is a good news, because if we have some data, we can artificially choosing the D, which control the dimension of our the input of our choice function model, which will for us to control the accuracy between the accuracy and between the efficiency of computation. And then there's some existing model which define the choice function on the CDFs, like in various two choice of theory or acceptability function. And later on, we'll show some example in the appendix if you are interested after the talk. Okay, so what we all deal with here is value problems. So we're introducing some sorting algorithms, which will be very computationally very elegant when we're dealing with quasi-compute choice. And also we talk about what is the effect of a law invariance. So now let's moving on to the main dish. So since we are doing decision-making problem, right? So we need to, finally, we need to do some optimization algorithms to make an optimal decision. And here is the, we need to study the interpretation problem. So here we propose two algorithms. First is a binary search algorithm, and second is called level search methods. So both algorithms working on interpretation problem, and they are rely on, we have already solved the value problem, or we have already know the approximate choice function value on this local information. So first is binary search. So the main idea here is we're using the concept called acceptance sets. So we know the idea of acceptance sets of risk measure, which meaning the minimum number we invest in the risk measure such that risk is lower than 0. So here is the same idea. So if we choose any value V, and then the acceptance sets of a robust choice function is the set of the prospects where the robust choice function value is higher or equal to V. And here is the idea of doing binary search. So given any value, starting level V, and we try to find some Z such that our random outcome is in the acceptance sets. So if we can't find such Z, then we increasing higher level search next. Otherwise, we search at a lower level until it converge, like a binary search. But we still want solving some linear programming or convex optimization problem which is retractable when we do the search. Yes, so here is the idea. So in Theorem 5, it tells us that we can see the next theorem first, the Theorem 5 first, meaning if we find a maximize, if we try to maximize the robust choice function, or meaning the maximization, or meaning the optimal value of this robust optimization problem is higher than some V, some level, and meaning the optimal value of some linear programming problem is larger than V, where the constraints of linear programming problem is defined in the Theorem 4. So this is also connect with the ordering in the sorting algorithm. So we first, if we choose some level V, it will give some value T by this mapping. So the T is actually tell us, what is the order, give us an ordered set. We know that if we compare the lowest value in the order set, it's actually the V is sitting between this T+1 and T. And this will give us polyhedron using the V value and construct the acceptance set, which is showing this formula, FVDT. And this is good because in this binary search, in each iteration, we are solving a linear programming problem. And this is Theorem 6 tell us the performance of this binary search algorithm, meaning we can find the optimal solution Z after O log J number of solving this complexity or size of a number of linear programming problem. And we can find the optimal solution. Okay, so this is binary search. So second thing is called a level search. This is another way of solving the optimization problem, starting directly from the interpretation problem side. So in interpretation problem, we were trying to find, okay, where the X, any random variable, where the the piece that the random variable sits. Okay, and actually what we do is we try to solve the single value B. This is a decision variable, but also the objective value. So our whole idea, our focus is on trying to find the optimal B. And okay, so now our idea is, can we get rid of the disjunctive term, and which will make our work easier. And we can show by this graph in the bottom part. Okay, and meaning that we have two functions. The first function is a linear function. Second function is a fixed function B, and meaning there's a mapping, one-to-one mapping between there's the linear part take effects, and also the V star theta is larger or equal to B. This meaning if we have we have already solved some value problem and we know the value on this local information, and if we give any value B, and all the sets of the local information which is a higher value than B, and then the linear function will take effect. And if it's lower and smaller than B, and it's only will equal to B. So then it meaning we can get rid of the the flat function part and only solve and focus on the linear function side. And yes, then the idea is we are trying to solving some actually unimodal problem on B, and we are doing a unimodal search on B and also on some theta B. Theta B is a linear programming problem, which will be done by some feasibility check. And the very interesting thing is we can prove that when we're solving a univariate optimization problem on unimodal objective and solving the original maximum robust optimization problem, they are equivalent. They're giving us the same optimal solution. So this is the structure of the algorithm, which is a linear search as I just described. So the seventh theorem, I think it is the last theorem of this talk, is telling us the performance of these level search methods. This meaning if we can find the epsilon optimal of this optimal solution of PRO, if we have run enough number of these level search, so the T here is larger than log of B minimum and ipsum. So the ipsum is something we decide, and then B here is the the interval of initial value of B, which is in B minimum and 0. So this is two algorithm we try to solve the the original maximum problem. Okay, so then we try to see some performance of our methodology by two real examples. So here we are trying to guide people for decision making. No one he know his choice function, no one his preferences, even himself. And we have some data-driven sets. So the prospects are all randomly generated and can be exposed to the decision maker. And as the process of preference robust optimization, the ECDS pair will be constructed. So two things we're interested to investigate. So if we do the decision clairvoyance perspective, meaning we don't know what the people's preferences and he don't know, but in the experiment we assume we know, and we formulate some perspective choice function. So the first thing is we want to show how good our robust choice function learn the true choice function of decision maker. The second thing is we want to show the how good our robust optimal solution in terms of his perspective value. So okay, and the perceived choice function we use is the expected is also optimal certainty equivalent. And so it's a certainty equivalent. And then we have two p's. So in the positive axis, so it is a concave function. And for the negative axis, it's a risk neutral, it's a linear function. And we have two versions, since we have both model on a random variable space and model on a CDF spaces. So the perceived choice function 2 is on the space of CDFs. So the first is so the capital allocation problem. There may be some words in the too much words in the stream. So the idea here is we try to allocate the scenario-based money into a random vector, which describe the financial status of institute, and they are generated. The current situation of the financial is randomly generated from systematic risk and some idiosyncratic risk. And our goal here is we try to solve the preference robust optimization problem, where we don't know what the perceived choice function is, but we have ECDS pair generated from the financial institute decision maker. And we have two goals. First, we try to test the sorting algorithm for the value problem. And also we test the performance of the binaural research algorithm, the first optimal optimization algorithm for the problem. So here is the first results, which show the scalability of the sorting. So the first part is on the sorting algorithm. The next bottom part is on MILP. So we see that if the ECDS pairs, we ask people to do 50 pairs of comparison. Okay, so MILP will use 30,000 seconds, which will very time consuming. But the sorting algorithm was using 1,500 seconds. But very interesting thing is if the ECDPS is very small, like 10, actually MLP will be faster. But this shows that the sorting algorithm has a much more strong scalability than some traditional methods.
Wenjie, we're planned to finish at 10, and I'd like to leave 5 minutes for questions. Is that
okay? I will finish as quick as possible. So this is the scalability of law invariance cases. So we see that for the number of attributes, the scalability is good because the number is increasing linearly with the number of attributes, but it does not good job in scenarios. So this is scalability of the binaural research, which will also show very nice scalability, the nice scalability on ECDS pairs and the scalability on the number of attributes. But still, there's a problem on the scalability of the number of scenarios. Okay, so this is an interesting graph showing the performance is robust choice function. So the left is seeing how good our robust choice value is varies with the number of the ECDS sizes. We see that if we consider law invariance, even we have a little information on the decision maker, it already gives a very accurate prediction. And the right part is giving us the perceived choice function value of a robust decision, meaning the decision maker don't know what he prefer, but we want to give him some plan, and he will tell us whether he like it or not. And we see that law invariance, you can see the law invariance will give a better decision than the model without law invariance. And for second is a portfolio optimization problem. Then we are working on the CDF spaces. We have some real financial data from Yahoo Finance, and we construct the empirical distribution for the daily outcome. So some findings, the third finding is we find a pure strategy always outperform any mixture strategy. Actually, in Eric's paper, we have some mixture quasi-concavity properties of a risk measure. And we also have this property, but we relax the condition because we do not enforce the translative invariance in our choice function. And also, this is the scalability comparison of the level search methods, then some level function methods, which is a traditional way of solving the quasi-programming problem. And we see that, okay, the level search method is very good. And even the number of decisions increase decision variable increase and the number of ECDS pairs increasing is very insensitive. And this is very interesting. So these results show the robust choice function also when we consider low invariance, even we have a little information of decision maker, still it learn the true choice function very well. And for the right part, we are seeing if we consider low invariance, the PR already give very nice perceived value, which close to the true perceived optimality. Okay, so this is all about the experiment outcome. So let me do a conclusion of this research. So in this research, we studied the PRO problems, a kind of a robust optimization problem where there's uncertainty in people's preferences rather than in rather than the distribution in robust optimization problem. We have uncertainty in the distribution of the systems. Also, our choice function here covers a number of well-known models, and we have some data-driven technique to handle the uncertainty about the preferences. So finally, our algorithm can be solved to solve the robust optimization problem and very strong scalability. Okay, thank you, and that's all my talk. And I attach some references and examples if you have any questions.